The body already knew. That is the part that is hardest to carry. Not in the way that grief gives you a retroactive sense of foreboding. The filtered memory of a look they gave you, a sentence you have replayed too many times since. Not in that soft, unbounded way. In a precise, measurable, electrochemical way. The body had already entered a cascade, a biological sequence that cardiologists can now trace backward. From the moment of the event, through the hours before, and find it there embedded in the data, like a fault line that had been under stress for a very long time, and had finally reached the moment of its resolution. The heart was already in conversation with its own catastrophe, and the person you loved, standing in the kitchen, driving to work, saying goodnight, was not lying when they said they felt fine. The conscious mind does not have access to the language the body speaks in those final hours. It never has. This is not a failure of awareness, it is the architecture of the system itself. In 1987, a cardiologist at Harvard Medical School named Dr. James Mueller published the results of a study called MILIS, the multi-center investigation of limitation of infarct size. His team had collected detailed event data from nearly 1,000 patients treated for acute myocardial infarction across 5 major American hospitals. The finding that emerged had not been the primary hypothesis. Heart attacks were not distributed evenly across the hours of the day, they clustered. Specifically, the incidence of acute myocardial infarction peaked sharply in the first 3 to 4 hours after waking, between 6 in the morning and noon, at a rate approximately 40% higher than at any other point in the day. The paper was published in the New England Journal of Medicine and has been replicated in populations across Europe, Asia, and North America in the decades since. The morning is not safer. It is, by measurable margin, more dangerous, and the body had already known this in its hormonal rhythms, in its hemodynamic patterns, every morning for years. That finding opened a door. If the timing was not random, then something biological was driving it, something that operated below the threshold of conscious experience. What researchers found in the years that followed was not a single cause, but a cascade, a sequence of physiological events, each one building on the last, each one making the next more likely, stretching backward through the hours of the night and sometimes the day before, into what had appeared, from every observable angle, to be a perfectly ordinary afternoon. The first part of the cascade begins with the body's own stress architecture. The human autonomic nervous system operates in 2 branches that are always in dynamic negotiation. The sympathetic branch, which accelerates, tenses, prepares the body for action, and the parasympathetic branch, which slows, restores, returns the system to equilibrium. In a healthy system, these 2 branches are in constant calibrated conversation. The result is visible in what cardiologists call heart rate variability. Not the steady beat of a metronome, but a living responsive oscillation in which the interval between each heartbeat rises and falls in subtle fluctuations. High heart rate variability is, across decades of cardiovascular research, one of the most consistent predictors of cardiac resilience. Low variability, a heart that beats with rigid, mechanical uniformity, is a predictor of risk. The data on this is clinically confirmed, measured in tens of thousands of patients, at institutions including the Mayo Clinic, the Karolinska Institutet in Stockholm, and the University of California, San Diego. What Holter monitor recordings reveal, the continuous 24-hour electrocardiograms used to track cardiac electrical activity over time, is that in the hours before a cardiac event, heart rate variability quietly collapses. The sympathetic branch gains dominance. The parasympathetic branch begins to withdraw. This shift is not felt as a symptom. There is no sensation that corresponds to the phrase decreased parasympathetic tone, or no alarm, no pain, no specific discomfort that rises above the noise of an ordinary day. The nervous system has moved toward a different equilibrium, and the body, from the outside, looks exactly the same as it did the day before. The sympathetic dominance triggers its own sequence. The adrenal glands release catecholamines, epinephrine, and norepinephrine, the biochemical signatures of arousal and acute stress. Cortisol, the longer-acting stress hormone produced by the adrenal cortex, also rises in the morning hours as part of the normal circadian rhythm of waking, a rise that occurs in everybody, every morning. In a body with no underlying vulnerability, this cortisol surge is unremarkable. It has happened every morning since the person was born. But in a body where atherosclerotic plaque has been accumulating inside the walls of the coronary arteries for years, the catecholamine and cortisol release does something specific. It increases the viscosity of the blood. It makes the blood thicker, more adhesive, more prone to the clotting behavior that is one of the blood's primary functions. This change in the blood's rheological properties builds across the hours of the night, into the morning, aligning with the body's own internal rhythms in a way that is almost architectural in its precision. The clotting mechanism that follows is not the obstruction that most people imagine, not a sudden blockage dropped into a clear pipe. It begins with a platelet, a tiny disc-shaped cell fragment, one of the most abundant elements in circulation, produced in the bone marrow at a rate of approximately 150 billion per day. In a healthy adult, platelets have one primary function: to stop bleeding. When a vessel wall is damaged, they rush to the site, adhere, and build a fibrin-reinforced plug. How a cut closes. Inside a coronary artery, where atherosclerotic plaque has been accumulating for decades, however, the vessel wall is not intact. The plaque, a complex of oxidized cholesterol, calcium, and fibrous tissue, is separated from the bloodstream only by a thin fibrous cap. This cap is, in the language of interventional cardiology, vulnerable. Under the hemodynamic stresses of the morning's cardiovascular arousal, the fibrous cap can rupture. This event, plaque rupture, is the proximate mechanical cause of approximately 70% of all acute myocardial infarctions, according to pathological analyses published across multiple decades in the Journal of the American College of Cardiology and arteriosclerosis, thrombosis, and vascular biology. When the fibrous cap ruptures, the contents of the plaque are exposed to the flowing bloodstream. The platelets respond. They aggregate. They release chemical signals, adenosine diphosphate, thromboxane A2, that call additional platelets to the site and activate the coagulation cascade, the enzymatic series that transforms soluble fibrinogen into the fibrin strands forming the structural matrix of a clot. In the space of minutes, a thrombus forms inside the coronary artery. If it is large enough to substantially obstruct flow, the myocardium begins to be deprived of oxygen. Cardiomyocytes, the muscle cells of the heart, begin to die at a rate measurable in the millions per hour in the affected territory. That is the infarction. That is the moment. But the rupture did not happen at the moment of the event. The plaque that ruptured had been accumulating for years, perhaps for the better part of a lifetime. And in the hours before the rupture, something was already destabilizing the fibrous cap, one of the more consequential and underappreciated chapters in the science of sudden cardiac death. Atherosclerosis is not simply passive accumulation. It is an active, ongoing inflammatory process. The plaques contain macrophages, immune cells that have infiltrated the arterial wall in response to oxidized cholesterol, and that release enzymes called matrix metalloproteinases, which degrade the structural proteins that give the fibrous cap its mechanical integrity. The more inflammatory activity inside the plaque, the thinner and more vulnerable the cap becomes. And the inflammatory activity within a plaque is not fixed, it fluctuates with the level of systemic inflammation circulating throughout the entire body. What researchers at the Karolinska Institutet and separately at Johns Hopkins have measured is that the serum concentration of C-reactive protein, a protein synthesized by the liver in response to systemic inflammatory signaling, and one of the most reliable available markers of inflammatory activity, is measurably elevated in patients who will sustain a cardiac event within the following 24 to 72 hours. The elevation is not dramatic. It does not reach the levels associated with acute infection. It rises above the individual's own baseline at a degree detectable in stored biobank samples, reconstructed retrospectively, but would not trigger any clinical threshold during a standard visit. The inflammatory machinery had already shifted its register. The macrophages within the plaque were already producing their enzymes at elevated rates. The fibrous cap was already under more biochemical stress than it had been a week earlier. And the person who went to sleep that night had no access to any of that information. It was not available in any form that consciousness can use. There is another layer to this cascade that neuroscience has begun to map, operating at the interface between body and brain with remarkable precision. The insular cortex, a structure folded deep within the lateral sulcus of each cerebral hemisphere, hidden from the brain's outer surface, is one of the primary neural substrates of interoception, the brain's continuous, largely unconscious monitoring of the body's internal physiological state. It receives ascending signals from the heart, the gut, the lungs, and the blood vessels via the vagus nerve and spinal afferent pathways, and integrates them into what neuroscientist Dr. A.D. Craig at the Barrow Neurological Institute called the brain's representation of the physiological condition of the body. Research by Dr. Hugo Critchley at the University of Sussex has established that insular cortex activity correlates with cardiac rhythm disturbances, that when the heart's electrical regularity begins to show the subtle arrhythmic precursors that sometimes precede an acute event, the insula registers the change, often below the threshold of conscious perception. The person does not experience the sensation of a premature ventricular contraction, but the insula has received the signal, and sometimes that registration propagates forward into conscious experience in a form so attenuated, so mixed with other somatic noise, that it surfaces not as a specific symptom, but as a quality. A vague sense of unease, an unlocatable restlessness, an anxiety without an identifiable source. In a study published in Circulation, Dr. Viola Vaccarino at Emory University analysed retrospective self-reports from patients recovering from acute myocardial infarction. Approximately 58% described unusual fatigue in the preceding 24 to 48 hours. Not tiredness from exertion, but a different texture of exhaustion, heavier, unresponsive to rest. 42% reported disrupted sleep in the nights prior. 22% described a difficult-to-locate sense of impending distress. Not a cardiac symptom, simply a registered signal that something was different, without sufficient resolution to be named or acted upon. The data requires methodological caution. Retrospective self-report is shaped by knowledge of what came next, but the neurological mechanism is consistent with what researchers understand about the insula, that the brain can register cardiac disturbance before the conscious mind can formulate it in language, before it rises above the noise of a day that, in every other observable respect, appeared entirely ordinary. This is the part of the cascade that is most difficult to sit with, not because it means something should have been different. The measurements that detect these signals are research-grade observations, not standard clinical tests, not something a physician routinely orders on a Tuesday afternoon. But because it means the process was already underway, the ordinary day was not, at the level of arterial chemistry and insular interoception, simply an ordinary day the body was signalling. Through the collapsed oscillation of its autonomic rhythms, through the elevated inflammatory chemistry of its arterial wall, through the deep interoceptive circuits of the insula, producing something that might have felt like unnamed unease. The question that lives inside the grief of sudden cardiac loss is whether any of that signalling could have been heard in time to matter. The honest answer from the science is almost certainly no. The signals were operating at resolutions finer than ordinary human experience is designed to process. The collapse in heart rate variability requires continuous electrocardiographic monitoring and specialized analysis to detect. The elevation in C-reactive protein requires a calibrated blood test ordered with that specific question in mind. The insular signal might produce unease. But unease is so common, so woven into the texture of ordinary days, that it cannot function as diagnostic information. The body was producing a signal. But the signal was, by design, below the threshold at which consciousness can act. This is not a design flaw, it is the consequence of what the system was built to do across hundreds of thousands of years of evolutionary pressure. If every fluctuation in every physiological variable reached conscious awareness at full resolution, the cognitive system would be overwhelmed within minutes. The filtering of those signals, the reduction of their amplitude as they travel from body to brain to conscious experience, is what allows a person to think, to be present, to occupy the ordinary moments that constitute a life. The filtering is the feature. In the context of a cascading cardiac event, It is also the reason the person could not tell you, not because they were withholding anything, because the body's knowledge and the mind's access to that knowledge occupy different territories, and the boundary between them is, by design, very nearly impermeable. Richard Feynman understood the relationship between what can be measured and what can be experienced with a precision that few other minds of his century matched. He was interested, throughout his career, in what it means to know something in the physical sense versus what it means to feel something in the experiential sense. These are not the same kind of knowing. In the letter he wrote to Arlene 16 months after her death, found in his personal archives 43 years later, only after his own death in February of 1988, he did not attempt to explain what had happened to her. He spoke to her as if the distance between them were logistical rather than fundamental, as if what had occurred were a change of coordinates, not an erasure. He ended the letter with an apology for not mailing it, explaining that he didn't know her new address. He was not being morbid. He was being precise, in the way that physics had taught him, acknowledging that what he could not measure, he could not map, but what he could not map was not therefore absent. The cascade that preceded the cardiac event of the person you loved was real and operating, and left traces researchers can identify in reconstructed data. The inflammatory marker was elevated. The autonomic balance had already shifted. The plaque was already under stress. It had not been under a week earlier. These are physical facts. They existed at specific times in a specific body, part of the physical record of what that body was doing in its final hours, of a person who was living fully in every conscious sense while the body moved, privately and without alarm, through its own sequence. The grief that lives in the gap between the body's knowledge and the mind's access to it does not resolve into anything simpler than it is. The science does not close that gap. It does something different. It makes the event legible at a level beneath intention and beneath experience. In the domain where the body operates entirely on its own, where platelets respond to chemical gradients, where the insula registers disturbances that the frontal cortex never receives, where the cascade runs its sequence regardless of what the conscious life layered above it is saying or attending to. The person did not know, the body knew, in the only language available to it. Pressure, chemistry, electrical gradient, the slow accumulation of a vulnerability building for years in a territory invisible from the surface of an ordinary day. The last conversation happened in the space that consciousness occupies. It was real in that space. It was complete in that space. The body's other story was happening simultaneously, in a different register, running its own conclusion in its own language. And between those two stories, between the language of the living moment and the language of the cascade, there was no bridge available. There was never supposed to be one. That is not a flaw in what was between you. That is the structure of what it means to be a body that is also a mind. Two systems, occupying the same coordinates, speaking entirely different languages, to the very end.